All right, good morning everyone. This is Anna Jenkins, Marketing Coordinator at Core BTS, and welcome to today's webinar, Data Centers Gone Wild, Part 1, a closer look at data center networking to address the needs of the business. Throughout our presentation this morning, we encourage you to interact with us by typing in questions and comments using the question and answer pane in the WebEx Event Center. We'll be answering questions live both during the event and after the presentation. We're also recording today's session, and we'll send a link to the recording after the event via email. Today on our panel, we have Tom Irvin, Core BTS Solution Architect, and at this time, I will pass this along to Tom to get us started.
Hi, Anna. Good morning. Thank you very much. Can you see my screen, by chance?
Yep. It looks like the presentation is there.
Perfect. Thank you. So good afternoon or good morning, everybody. My name is Tom Irvin. I'm a Solutions Architect here at Core BTS. Focusing on data center architecture as well as routing, switching, wireless, essentially anything in the Cisco portfolio that is non-UC or video. So I'm all over the board on the Cisco portfolio, but today we're going to focus on some data center technologies and talk a little bit about some application-centric infrastructure as sort of a high-level overview. So today's agenda, we're going to talk a little bit about the business requirements in the data center, how those have been changing over the years. We're going to go into sort of overview of the evolution that we've seen in the data center based upon architectural differentiations based on, more and more footprint on virtual machines. And then we're going to talk a little bit about Cisco application-centric infrastructure, ACI. We're going to do a component overview. It's going to be sort of, enough information to give you a 30,000-foot view of what ACI is. We're not going to go into excruciating detail on the ACI technology, but we encourage you to do so afterwards. This is supposed to be sort of a high-level primer, if you will, to get your foot in the door on the ACI architecture from Cisco. And then we're going to talk a little bit about the benefits of ACI, sort of see how it works from the application point of view and how we can implement that in our data center. So business requirements in the data center, we know those are always constantly changing. Essentially, what we're seeing is trends. Of course, we have to do more with less. So I'm not going to read this entire slide. However, we see a few key pieces in here, which is, we need to have business agility. We have to be able to go from development to production in a timely manner, seamlessly if possible, right? So business agility. Cloud integration. A lot of our customers are either doing full cloud or hybrid cloud. And in that case, we need to make sure our customers are positioned in their data center to support cloud infrastructure, be it hybrid or 100% cloud or internal cloud. And then, of course, the price, right? So we want to make sure that whatever we're putting in the data center is going to help reduce the cost of the ever-shrinking IT budget, right? So hopefully today we'll have some more input into how the cost can be reduced. So when we look at an application, it could be an application that's in test dev and wants to go in production, but it could be an application that's in production. But we see that an application from the application point of view has certain requirements, right? It's more than just a server. It's more than just a virtual machine, right? It's usually a set of virtual machines or servers and services that have to be associated with it. So, for example, we have a collection of application endpoints. In this case, the external network needs to talk to, the web tier, which is an application tier, right? The web services group. Before it goes into the web tier, we're going to do services, maybe load balancing, maybe some security, maybe some QoS. And then as the web tier talks to the application tier, we see that we have to do some services between those two tiers as well, right? And typically, web tier communication to application tier communications could be either one direction or bidirectional, right? Two-way conversations. And then the app tier needs to talk to the database tier to get some information, right? simple example, right, of relationships between applications. There's really no reason for perhaps an end user on the external network to talk directly to the database tier, right? So that might be a security issue. So we need to make sure that whatever security features are put in place as far as policy goes, we take into account the security between these different types of tiers. So this is from the application point of view, right? The other end of this is the network people who have to enforce this policy and security and make this illustration as far as relationships go match up to the command line configuration within the switches and routers and firewalls and servers within the network, right? So what we see that there's really two types of languages being spoken when we're trying to deploy an application. We have the application developers who have certain requirements. They have SLAs for the applications. We have response time requirements. We have security requirements. And we have, compliancy requirements. And when it's pulled over to the network people, they have to translate all these requirements into things like VLANs, firewalls, QoS policies. And they have to configure that on the network. Usually not on just a single device. It's usually within devices throughout the network, because what we see is, traffic is going from point A to point B through the network, and it has to follow certain policies. So it's up to the network engineers to make sure that these application policies are being followed. So what we end up is communication breakdown, right? So that usually takes time out of the development production cycle because when we want to implement an application on a network, we have to take into account all the activity that has to happen on the left side, so which can take a lot of time when you think about it. So evolution of the data center architecture, right? So the data center has been changing over the years. In the early days, 10 years ago or so, right? So we started talking about, access, aggregation, and data center cores, right? So this is a simple illustration showing that, the servers would connect to the access layer, the aggregation would apply policy, for example, and the core would be doing a lot of the layer 3 traffic management, right? So this structure, simple as it looks, it can get complicated. So if we have to add additional pods or blocks of data center aggregated information or servers, switches and servers, we can see that it can scale by adding blocks to a single core. This typical 3-tier design can actually scale rather large, right? And if you actually flip it upside down, it can look like a tree. So this is typically and often discussed and described as a tree architecture in the data center. And we can see that in order to get from a server, in order to get from a switch on the left side of this image over to a switch that's server that's connected to a switch on the right side of the image, it has to go through multiple hops and multiple devices to get there, right? So it really comes up to a lot of issues when we're talking about the tree topology, right? Configuration is complex because there's a lot of devices between point A and point B that need to be configured in order to enforce the application requirements, right? It's error prone because there's a lot of hands-on CLI configuration and a lot of touch points, right? So it's really difficult to quickly adjust the network configuration to support applications, right? And it's not cost effective, right? So if we run out of resources in the core, we have to add additional hardware in the core, and that typically is not a cheap endeavor, right? So it's going to add up, right? So you're going to have capital expenses, required to increase the scalability of the core. Right? Additional challenges is sort of sprawl, right? I found this diagram because we want to focus on the way the traffic is flowing through early architectures, right? So this tree design is really developed for north-south traffic flows, right? Server A talking to server B, and server A is on the left at the bottom, server B is on the right at the bottom, it has to go up, over, and down, right? That's a north-south type traffic pattern. And we can have a lot of these data center pods connecting to the core. We can have challenges with things like link congestion and delays and the traffic congestion based on consolidated traffic flows into individual links, right? But we see now that because server architecture has become more and more virtualized, we see more east to west traffic flows, which would be from switch to switch within a data center, right? And or server to server or server to storage, right? So a lot more traffic flow is going away from north-south, and it's becoming more and more east-west, just based upon the fact that there's more and more server virtualization in the environments now. A lot of our customers are 100% virtualized. A lot of our customers are 15, maybe 20% not virtualized, and they want to get to that final stage. And some customers have applications that they cannot be virtualized at all. But the whole idea is that more and more server infrastructure, of course, is becoming more and more virtualized. And there's multiple hypervisor environments, right? You got Hyper-V, VMware, and so on. And so, so it's becoming more and more prominent in the data center to have more and more virtual machines, right? And so when we're talking about the classical architecture of a chassis type environment, right, we have a couple challenges. It requires prediction on the designer's part, the customer's part, because we have to pick a chassis platform that can scale to what they need, and they need to be able to have the port density that they need, not only now, but in the future. But what we see is when we're choosing a chassis, either a 6500 or maybe Nexus 7K, right, there's maximums within the chassis, right? There's port maximums. You can only have a certain maximum number of ports. There's also I/O performance maximums. In the 6500, it's related to the SOUP engine, and the Nexus 7K is related to the fabric modules, right? And the big question is, what should I purchase now in order to suit my data center needs in the future, right? And that's often very difficult to do because you're not sure, A, where the technology is going on the server side. We're not sure what the volume traffic is going to be future. Now we're doing 10 gig and 40 gig, right? We want to be positioned for potentially 100 gig because we want to keep the hardware, in production for a long time to get, the most bang for your buck, right? So you want to make sure that whatever you're getting is going to scale. So for example, Nexus 7K, right? There's multiple form factors of this chassis, and it scales with throughput by adding Fab 2 modules or fabric modules. So you can have a certain number of fabric modules per chassis. The more fabric modules you add, the more throughput you get within the chassis. And that's good to a certain point, right? Because you can start off with maybe 3 fab modules and then scale up, add a couple more as your needs are, as you need more I/O. However, there is maximums within these, right? And if you need more ports, you add more line cards. That too is there's a hard stop there in a chassis as well because you can only add a certain amount of line cards. In the Nexus 7K, you can't add fabric extenders to extend port density, but the challenge there is that we still have we have links, 10 gig links or 40 gig links going up to the Nexus 7K chassis, which can be oversubscribed. So the more things you hang off of the chassis, the more throughput is being consumed, right? So the whole point I'm trying to show here is that we have hard stops, hard levels at both performance and port densities. So one of the newer architectures is leaf spine architecture, right? Instead of going the hard chassis route, leaf spine is really based upon port density and performance. Spine switches, you can think of those as fabric modules in a chassis environment, right? So if we want to add more I/O to our leaf spine environment, we can add more spines. If we wanted to add more port density, we could add more leaves, right? So the leaf switches in an environment are the switches that connect to our endpoints. That's going to be our servers, our storage, our firewalls, our devices that are classically connecting to a switch in an environment, right? And then our spine switches typically are high throughput, high density switches that can take the links between the leaf spine and the leaves and the spine, right? And you can see in this scenario we have 2 spines and we have 2 leaves, right? In this case, if those were 10 gig links, each leaf would have 20 gigs of throughput to the next leaf over, right? This is focusing on east-west traffic. So if we have servers, either physical or virtual servers, on the left leaf, and physical or virtual sort of servers or resources on the right leaf, we know that the left leaf can talk to the right leaf through a predetermined amount of bandwidth and latency, because each leaf is exactly one hop away from each spine, right? And some of the rules that we could go by are spines only connect to leaves. We don't connect spines to spines. Leaves only connect to spines. So we are connecting each leaf to every spine in the situation, right? Every spine is connected to every leaf, and every leaf is connected to every spine. Every spine is one hop away from each leaf. So if we look at this, and if we do the math, if these were 10 gig lengths, in the leaf going up to the spines, we would have 48 ports on the left leaf being provided 20 gigs of bandwidth for the fabric, right? And so there's an oversubscription ratio of 24:1, right? If we add more leaves, if we add more links between the leaves and the spines, then we can increase that or decrease that oversubscription ratio. So if we had 4 10 gig lengths per leaf going up to the spine, then we would have a total of 12:1 oversubscription. If we had 8 10 gig leaves, we could have 6:1. If we had 16 10 gig leaves, we could have 3:1 oversubscription, right? And so as we add more links between the leaves and the spines, we can reduce the oversubscription, right? The challenge here is if we're going 10 gig on the connections between the spine and the leaves, then we can eat up the ports relatively fast in the spine switches, right? Which is one of the benefits of some of the newer technologies where we're going up to 40 gig and potentially 100 gig, right? So in summary on this slide, if we wanted to add more bandwidth to the environment, we could either add more links or add more spines, right? So need more port density, add more leaves. Need more throughput, add more spines or more links from leaves to spine, right? And so it can scale out. So in this diagram, we keep scaling out to the right as we add switches, as long as we follow the rules that every spine, every leaf is connected to every spine. Right? And it scales. This is sort of an eye chart, but the concept is there, right? So these are probably Nexus 3Ks in the leaf section, and these might be 7Ks at the spine section. Who knows, right? But the whole idea is that every leaf is connected to every spine, and the spines are not connected to each other, and the leaves are not connected to each other. The benefit of this architecture is that you know exactly the distance from every spine to every link as far as throughput and latency, right? So in this scenario, we have a certain number of leaves connecting to whatever the number of spines are, and those are 10 gig lengths. So you can see how sort of cable intensive it would be if we're going to go to 10 gig lengths. We can reduce all that infrastructure by going from 10 gig lengths to 40 gig lengths and maintaining the same throughput within the fabric. So some of the benefits of leaf and spine, I touched upon these earlier. You know, it provides a flexible fabric that can scale in both bandwidth and port counts. So you could start off with, you know, 2 leaves and 2 spines, and as your data center grows, you can add more leaves and more spines as needed, right? So you can start very small and grow as needed. Very deterministic behavior as far as latency goes, right? Because each leaf is one hop away from every spine. We know that we can reach, you know, a different leaf by multiple paths, right? So the benefit of that is that you can use equal cost multipath technologies to sort of use all the bandwidth available to that other spine or other leaf to make sure that the data gets there in a timely fashion under specific QoS rules. And it's designed for east-west traffic, right? Predictable traffic flows. So virtual machine to virtual machine, virtual machine to server, server replication, east-west traffic is ideal for this type of integration. And it easily integrates in your existing data center networks. I might have a diagram on this later, but you could start your existing small leaf spine architecture topology, and you could tie it into your existing tree architecture. And then as you age out your tree architecture, you could increase the size of your spine architecture as needed, both performance and port density. So sort of a summary slide here, right? Evolution of today's data center fabrics, right? So over on the right side, left side, we have, early times, right? So we're still doing a spanning tree, right? We're losing half the lengths, right? In the middle slide, we're doing virtual port channels, VPCs, right? We're using more bandwidth. We're using all the lengths in the northbound fabric, right? And then over on the right side, we have spine and leaf fabric, right? So between the spines and the leaf, we do have a dedicated fabric that's predictable as far as latency goes. Which brings us into application-centric infrastructure, right? So we talked about the early days of data centers and the migration to, the traffic migration to east-west from north-south as far as characteristics go, right? And now we talk about application-centric infrastructure, or ACI, right? ACI is a object-based solution to help speed up the configuration of a network, as well as look at the network requirements from an application level, right? Going back to that slide where I had the communication breakdown between the application developers and the network guys, right? ACI solves that problem, right? So what is ACI? It's a policy-based network model that is looking at the network from the policy requirements of the application, right? It's simplified topology based on the leaf spine topology, automatic infrastructure provisioning, scalable, it's secure multi-tenancy. And tenants might not be different companies within a data center, they might be different organizations within a larger organization, right? Security is key, so ACI in the leaf and spine architecture by default is a stateless firewall, meaning that nobody's allowed on the network unless there's a policy that says so, right? It's cost effective, simplified operations, so a lot of the detailed configurations of networking devices are done automatically by the ACI management controller. And there's a broad ecosystem of partners that can tie into the ACI infrastructure and implement it according to what they need for their development. I'll go through a couple examples of that. So I brought this slide in. I put this in for a reason, right? If you're familiar with Cisco Unified Computing System, or UCS, there's a concept called service profiles, where for example, a UCS B-series environment, service profiles actually virtualize the characteristic or the identity of the server away from the physical hardware. So for example, whatever makes a server unique in an environment, might be MAC addresses, it might be BIOS levels, it might be firmware levels, it might be WWNs, UUIDs, anything that makes a server unique on a network in an environment can be virtualized in a service profile. And so if we have a server in a UCS environment that has a certain service profile, certain MAC address, and we're running SQL on top of that, right? And that server actually, the physical hardware dies. We can actually move the service profile of that dead server and apply it to a totally different piece of server hardware in the Cisco world, and SQL server riding on top of it would not know the difference that it's on different hardware. So service profile takes the identity of the server, the network policies, the storage policies, and the server policies, and virtualizes it, makes it stateless, right? We're doing something similar here with Cisco ACI, right? We're making the network a stateless network. So, one of the challenges that networks have is, there's a lot of things to configure and a lot of touch points to be considered in order for applications to work, right? We have network policies, such as mark, tag, redirect. We have subnets. We have VLANs. We have layer 4 services, layer 7 services, IDS, IPS, security services, quality of services, and high availability. All these things have to be taken into consideration when we're talking about applications and their requirements on the network. Right? So this is what all the network folks have to worry about really when we're rolling out applications. So what problem does ACI solve? I could have had a list of things down here saying exactly what it solves, but I put this picture in here just to sort of show a point, right? There's a network behind there, and you see different VLANs and different components, different web servers, different touch points, right? So all those touch points have to be, in some point, configured in order to support initiatives, or if the network changes, or if we have application changes, right? All those have to be configured, right? And ACI does this for you on an object-based policy model. So it takes a lot of the guesswork out of doing these configurations. Some key components to ACI for application-centric infrastructure. The Nexus 9K switch is the platform that runs ACI. It's in ACI mode. It's leaf and spine topology that we discussed. There's an application policy infrastructure controller. It's called an APIC. This is the manager of the policy on the network, right? This is the device or the element of the ACI environment that allows us to configure the network based on policy, and allows some of those ecosystem partners to configure the network on their behalf based on policy, right? Then we have a concept called endpoints. Endpoints are servers, services. They are unique items within an environment that require similar policy. And we'll touch upon that in a second. And then we have something called an ANP, or Application Network Profile, right? This sort of puts it all together as far as how can the pieces within an application talk together, what are the rules, what they can do, what they can't do. That's all done within an Application Network Profile, which is equivalent mentally to your service profile in the UCS world. Right? So the Nexus 9000 platform is the architecture based for the ACI environment, right? There's chassis-based and there's fixed form factors, right, depending on the scalability of what you need. They are great switches if you're not ready for ACI yet, because you can run them in regular Nexus OS mode and go to the ACI mode later, so it gives you flexibility as well. So here's the switches. Two different types of operation models, right? Investment protection, right, towards ACI. So you might want to start with a spine leaf type of architecture or traditional 3-tiered architecture that allows you to go 10 gig, 40 gig, 100 gig scalability in the hardware. And then later down the road, you can convert that over into the ACI mode, right? ACI mode is a software change, and it allows the fabric, leaf and spine fabric, to be controlled and communicated by the APIC controller, the Application Profile Information Controller. Okay? So two different modes. Definitely something to think about as far as investment protection, going from classical over to the ACI mode. So again, NXOS is a standalone mode, or NXOS mode, right? CLI that everybody's familiar with. It's programmable to a certain degree, 40 gigs at the cost of 10 gigs. They mean what's new in the hardware, 40 gigs at the cost of 10 gigs. That's based upon the optics, right? So 40 gigs in the data center requires single mode fiber. Cisco has these optics called BIDI optics that allow you to run 40 gigs over 10 gig OM3 fiber, right? So it allows you to run 40 gig within your network, data center network, without the requirement for upgrading the fiber within the network. Power efficient. And the second mode is ACI mode or fabric mode, right? So this is ideal for multi-tenant environments. It allows the APIC to configure the fabric for you, right? And it has great QoS methods as well as atomic counters and health scores. So the APIC allows you to troubleshoot a lot of the issues that you might see in the network. If you're not sure if it's the application people say it's a network people say the network's fine, it's the application. Right? So the APIC can help you with that in the ACI mode. Here's a sampling of the Nexus 9K switches. Right? So if you look over on the left, we'll start with the leaf switches, right? High density, 10 gig southbound connectivity, right? So the bottom left switch has 48 10 gig ports, and it has 2, 4, 6, 8, 10, 12 northbound 40 gig ports. Half of, I believe, are used in that model. But you can have 10 or 40 gig northbound connections to the spine switch. We recommend 40 gigs. And above that is the 93128 TX as a 10 gig RJ45 leaf switch with, in that case, you can use all the 40 gig ports northbound to tie to your spine switches. Right? In your spine switches, you can see the 9336 PQ is just a switch with 36 40 gig QSFP ports. Right? Typically, you might have 2 of those as your starter kit into a spine, leaf and spine environment, right, for redundancy. But you can see the more leaf connections to the spine connections you have, the more ports you're going to be eating up. So that's something to consider when you're thinking about your oversubscription rate at the leaf level through the fabric. And then the chassis. The chassis can be leaf switches. Certain chassis blades can be spine switches. Just depends on what your requirements are on the chassis set. So preparing your existing network. We talked about migrating from your existing network over to your leaf and spine topology, ultimately perhaps the ACI environment. This is one way you potentially can tie it into it, right? So over on the left is your tree architecture, your classical layer 3, 3-tiered environment, right? We can tie into it at the aggregation layer your 9K leaf switches, right? And those servers on the left can communicate with the servers on the right. You can see over, if we wanted to go to the ACI route, then we would have to include our APIC cluster, our application controller information, application policy infrastructure controller. I like to say APIC, right? It's a lot easier. And they would help manage the fabric. There we go. The application policy infrastructure controller, the APIC, right? Physically, it's a C220 M3 or M4 server, right? And it's running software. There's 3 of them on your fabric for redundancy. The database that it stores within the APIC is actually shared in redundant fashion across all 3 in a technique called sharding. And that allows the event of a single controller going down. We still have, we still can manage the fabric, right? So that's a cluster of 3 APICs within an ACI. It programs and maintains the ACI fabric. So it is looking for items such as delay, latency, links down, that type of thing, as well as management and pushing out policy into the environment. And the APIC itself, we talked about our northbound third-party ecosystem partners, right? So REST API architecture is what the APIC is founded upon, which is an open architecture. And APIs, the REST APIs, are used to hook into third-party applications, right? Many of them out there, the ecosystem keeps growing. The one that I'll talk about would probably be Cisco Data Center Manager, right? Where we would like to make changes throughout the entire stack of the data center, from VMs to storage to the networking, right? And that is done by tying into the REST APIs within the APIC infrastructure. And so again, back to this, right? So virtualization of the network, right? So the application profile, which is what we're going to talk about a little bit, is really equivalent to the service profile on the UCS environment. So here's our northbound ecosystem partners I've been talking about, right? A lot of these guys can tie into the APIC through the REST API and have their software tell the APIC to make the changes on their behalf within the fabric and apply those policies as needed. So a few terms, right? ACI endpoint groups, we talked a little bit about that, right? The endpoint groups are really a collection of similar endpoints, right? It could be a tier of an application, for example, web servers. It could be a group of shared services, such as DHCP or DNS, right? It's a logical grouping of objects, a similar function, and more specifically, a similar policy. So some examples of endpoint groups, right? Endpoint group users would have certain rights and require certain policies. Endpoint group database, web app, right? Similar tier, you get endpoint group could be a subnet, a VLAN, a VNIC, a VMware port group, or a set of services such as DNS and DHCP. That's all identified and configured by the APIC. And so here's an example. Endpoint group, right? Towards the bottom, we have endpoint group web. This is for, this potentially could be for an individual tenant, right? So customer A has a web presence, right? So they're going to have their web tier. Those guys require a similar policy. And then the web tier has to talk to the app tier has to talk to the database tier, right? And what we show here is that they're directly connected. That's slightly incorrect because we know that we want to put policies and rules between the web and the app tier and the app and the database tier. And we want to make sure that the web tier doesn't talk directly to the database tiers because it has to go through the app tier. That's based on policy that you've set, right? So we come up with something called, in this illustration, it's called a policy. In reality, it's called a contract, right? So endpoint group B talks to A, or the blue group talks to the red group through a policy. The red group talks to the orange group through a policy, right? So let's create an application network profile, right? So you need to identify your source endpoint group and your destination endpoint group. You have to create a policy, which is permit, deny, log, copy, redirect, et cetera, whatever the rules are that you want to apply to the traffic between endpoint group A and B. And create connection points between the two. This is known as a contract. Contracts are rules that say endpoint group A has to follow these rules in order to talk to endpoint group B. Right? So the rules can be anything from permit, deny, redirect. Maybe you want to send information or send traffic before it gets to the application level over to a load balancer, maybe push it through a firewall, right? Maybe push it through an IPS. So those are all defined within the contract. So here's an example of application network profile. Right? Application network profile, we have the users that are going to be consuming resources from the web farm. The web farm has a two-way contract with the application server, so they can talk back and forth. And the database tier or database endpoint group is serving up resources to the application server. Right? So that's sort of a high-level overview. Contracts can be defined as one-way or two-way between endpoint groups, and they can be very general as far as basic, only ports 80 and 443 can go through, or they could be as detailed as possible, making them go through services such as firewalling, load balancing, and other security services. Here's a sample, right? Again, this is a three-tiered application with web application database with a contract between the two. Here's one a little bit more complicated where we have, all the endpoint groups, web, application, and database should be able to talk to management, the management network, based on the contract. right? And then web, application, and database have a contract that has two-way communication to the endpoint group NFS, or storage tier, right? And you can see that the end user in this case has a two-way contract with the web group based on those arrows. And based on policies would depend on what endpoint group can talk to what endpoint group, right? These are all identified in the APIC, and this is based upon the stateless firewall feature of the ACI fabric, meaning that nobody can talk to anybody unless the policy says so, right? And just the redundancy of this slide, virtualization of the network piece. So some benefits of the ACI. You can scale, right, just by adding leaves and nodes. Right now, ACI, I think, can max out at 8 nodes, but we see that the port density on the leaf switches is such that you could have a high density of user or server ports, right? It allows you to transition to 40 gig if you're not at 40 gig, so the 9K hardware allows you to transition easily to the 40K. It allows you, the ACI, and the APIC specifically, allows application performance troubleshooting, right? Is it the application or is it the network? What's causing the trouble? It does a atomic counter, so it does count packets and bits throughout the network, right? High availability. The fabric is high available because we have, you know, 2 spines, at least 2 spines, hopefully, right? In case one spine goes down, we're still up. And the APIC itself, the application policy information controller, is not in the data plane. So if the APIC cluster went down for whatever reason, data would still flow, but we couldn't make any changes to the fabric, right? So key point that the APIC's not in the data plane. And another benefit of ACI is that any endpoint, either physical or virtual, doesn't matter. Any hypervisor, it doesn't matter in the ACI architecture. Here's a screenshot of sort of the health scores that the APIC can provide, right? So it's counting packets, it's looking for congestion, it's looking at buffers, it's looking at all the details of the traffic flow, and it gives you an idea of, okay, is it actually the network or is it actually the application that might be causing the problems? If the APIC comes back with a good health score, chances are it's probably the application. And additional benefits of ACI, of course, business agility, because you can actually create your application network profiles for testing and development, and then when it's time to go into production, you could just migrate those application network profiles on the ASIC over into the production environment, and you're up and running in your new environment with the same contracts, same SLAs, same characteristics and endpoint groups as was created in the test dev environment, right? Lower capital expenses, right? So we're using less time configuring and troubleshooting because the APIC is actually doing a lot of heavy lifting for us, right? And the 9Ks themselves are very cost competitive compared to some of the larger chassis such as 7Ks, right? Lower operating costs as newer hardware is more efficient. We're using 40 gig links, for example, reducing cabling, increasing airflow, and it's designed for east-west traffic optimization and can scale as needed. So, a lot of places to go to learn more about ACI, right? Some of them, reading white papers is one thing, but I learned that probably the best thing to do is get caught up on some ACI Cisco videos to help explain whiteboard sessions. It puts a lot of these concepts in your head consistently so that you're used to talking the language, right? the YouTube/Cisco channel, cisco.com. ACI design guides are good. White papers are great. And of course, cisco.com/go/ACI. So now, Anna, that's all I have right now. Do you want to see if we can open it up and see if I could field any questions?
Sure. So if anyone has questions, please feel free to type them into the Q&A box here in the Event Center. Tom and I will stay on the line for a little while here to help answer any questions you may have.
Nothing, Anna?
Doesn't look like it. So
Okay.
On behalf of myself and Tom and the rest of us here at Core BTS, we thank you for joining us and taking time to view this presentation this morning. If you have any further questions, please reach out to marketing.team@Core BTS. And to register for part 2 of this data center webinar series, please visit the events calendar on our website at www.corebts.com. Part 2 will cover the user-defined network and disaster recovery and business continuity. So thank you very much, everybody, and hope to talk to all of you soon.
Thank you.